set of vectors, okay, and define certain structures on the set of vectors which will help us to in many physics applications. Okay. So in my next object that I would like to define is a vector space. We require the following quantities for defining the vector space. We require V, set of vectors, okay. And then we require a set of scalars. In fact, call this as the field of scalars. Field is an algebraic structure, the field of scalars. And then you require two binary operations. One is, I call this as plus. This is vector addition. At this moment, I will call it a dot, which is called scalar multiplication. So we require a set of vectors, a set of scalars, a vector addition, and a scalar multiplication. An algebraic structure V, F, plus, dot. Vectors, scalars, vector addition, scalar multiplication. This will form an algebraic structure. Is a vector space if and only the following axioms are satisfied. It has to satisfy certain axioms. So what are those axioms that need to be satisfied? First axiom: if you take two vectors for any, let me maintain this notation for some time. For any vectors u, v in V, u plus v should also be written. This is called closure under vector addition. This is called closure under vector addition. That means you should not take two vectors from the space, add them and produce a vector which does not belong to that space. Then you say that it is not closed, it is taking it out of the space, right? So such a thing should not happen. Every two vectors you take, when you combine them, add them, you should get a vector within the space, within that set. Second property is that for every W in V, U plus V plus W is the same as U plus V plus W. This is called associative. Vector addition is associative. Associative. There must exist a null vector zero V such that 0 plus V is equal to V plus 0 is equal to V for all V this is called existence of a null vector or existence of an additive identity. Null vector is also called additive identity.
What is the physical significance of
Concept. That's the concept of null vector.
Null vector means the vector which adds nothing to any other vector.
in space?
In space, the vector which has a zero magnitude. Every component is zero.
That means it's a point. Arbitrary point in space.
It will be the origin. Any point you see, if you anything about the components you can talk only if you choose a coordinate system. So null vector will be origin of every coordinate system that you choose. If you want to view it geometrically, null vector will be origin of every coordinate that you choose. Origin will be a vector with components 0, 0, 0. So such a vector should exist. Then only you can talk about a vector space. For every V in V, there must exist minus V in V such that plus minus V is equal to minus V plus V is equal to null. This is called existence of additive inverse. So minus V is the vector additive inverse of for every pair of vectors, for every U comma V in V, V plus V. This is called commutativity. Commutativity under vector concept. These are the axioms that need to be satisfied with respect to vector addition as a binary operation. Now, you may know any set with a binary operation, if it satisfies these 5 axioms, that set with that operation is called an abelian group. Okay, if it satisfies only these 4, it is called a group. If it is also satisfied, it is called an abelian group. Okay, so this implies that V plus so axioms 1 to 5 satisfied by set of vectors V with vector addition implies that V plus is an abelian. So it may be easy to remember that V f plus dot is a vector space if V plus is an abelian. V plus has to be necessarily an abelian. Okay. So when you say V plus is abelian group, that means all these 5 will automatically come into picture. 6. So we have already completed what are these vector addition. Now let's go to scalar multiplication. For any alpha in the set of scalars and V in set of vectors, alpha dot V should be in the set of vectors. This is called closure under scalar multiplication. Closure I don't know whether closure is 1s or 2s, sometimes it is 1s. Scalar multiplication. Closure under scalar multiplication. For any alpha in F, U comma V, alpha dot U plus V is equal to alpha dot U plus alpha dot scalar multiplication, this is called distributive problem. Scalar multiplication is distributive. So if any vectors, if any algebraic structure made up of set of vectors, set of scalars, vector addition and scalar multiplication satisfies these 7 axioms, 5 with vector addition, 2 with scalar multiplication, we call this algebraic structure a vector space. Okay, so these are the axioms. So if someone gives you a set and then asks you, tell me whether it's a vector space or not, you have to religiously verify these 7 axioms. If any one of this is not satisfied, then that fails to be a vector space. Is that clear? This is the definition of a vector space. Sometimes in textbooks you will see the mentioning of linear vector space. Actually, there are no non-linear vector spaces, so it's an additional adjective. So vector space is always a linear vector space. So I will not worry about adding the term linear again and again because we don't have any non-linear vector spaces. So vector space is always a linear vector space. Okay, so this is the definition. So writing down the definition is the first step.